let's get started with compute layer unbundled, and I will only leave a link for every one of you to the next webinar. Next webinar, also Marek will tell it in a few words, at the end of this webinar, but I will leave the link also in chat, so you could sign up. And the next one will be AI-assisted engineering in the Open Data Lakehouse. But let's get back to this one. And this one will be about compute layer. And our today's speakers are Marek Wiewiórka and Radosław Schmidt, and I'll leave voice to them.
Thank you for the introduction. So let's get started. Maybe start with the quick recap of the previous episodes, previous session, because as already mentioned, this is the 4th episode. But as a recap, we already got three episodes. In the first one, we got a quick introduction to the data lakehouse architecture, so the construction of the open data lakehouse approach. Next, we discussed the storage, those things like open file table formats and some optimization hits for the layouts. The last episode we had was about data catalogs, when we discussed the technical versus business ones, open source and managed, and all the challenges with building an open data lakehouse architecture using both proprietary and open source catalogs. And finally today, today's episode is dedicated to the compute layer. So as you all know, this is the third building block, third pillar of the data lakehouse, together with data catalog and storage layer. Over the past episodes, we tried to make you aware that today's open data lakehouse architecture is kind of composable. We started from different storage layer, different storage formats and table formats. We also discussed that the metadata layer is also modular and composable nowadays, meaning that we have a few options when it comes to metadata management. We got this business and technical catalogs. And finally, today, we're going to focus on compute, which is even more composable. We have even more options to choose from. Today's presentation will consist of two main parts. In the first one, I'm going to deep dive in the current market trends from the technical perspective. So we present how the compute layer is evolving nowadays. Whereas in the second part of the presentation, Radosław will discuss some more details, the deployment options that we have. Okay, so when we zoom in and take a closer look at the compute layer market trends, we can easily observe a few ones. So first of all, both Python and SQL seems to be a primary end user interface, and you no longer can say that one of them is predominant. In our opinion, from the project that we are delivering, most of the customers tend to use both, depending on the problem, depending on the role that given end user is playing in organization. We're also observing that there is some evolution in the data frames, in the single node data frames ecosystem. So we observe some more visible migration towards lazy and out of core processing within data frames tools. So many companies start using, for example, Porous projects instead of Pandas. I will go into much more details about lazy and out of core processing later on. At the same time, we are also observing the emergence of HPC single node engines such as DuckDB, Polars, or Data Fusion. Next, there is a couple interesting projects with the goal of accelerating or providing an acceleration layer to the Apache Spark distributed engine. There are projects like Apache Data Fusion Comet, Poton, that is a proprietary one provided by Databricks, Apache Auron, or Apache Gluten. They're all of them try to add a kind of native accelerators for Apache Spark. So Apache Spark itself as a tool is evolving nowadays extensively. We are also, as mentioned, observing a shift from like a JVM based solutions, tools towards native ones. And it can come with into two flavors. One, as already mentioned, as a kind of native accelerators to already existing tools like native accelerators for Apache Spark or Apache Flink. Or we also observe the rise of like engines that were from ground up written in a natively compiled languages such as C++ or Rust. And there are projects like Daft, Polars, or like we are also discuss them a bit later on. And finally, we also observe variety of deployment options. That is something that Radek is going to discuss next. But the two more concepts that I would like to introduce you and show you how it's actually how they are evolving are modularity and composability. So we can observe that right now data systems are evolving from like a monolith. So like you can think of like an all-time database system that everything was tightly coupled towards really modular data stacks. And we can observe that at different levels. So first of all, we can, going from top to down, we can observe that this decoupling is at the very high level at the data lakehouse architecture. So with the data lakehouse, you have a clear separation of storage, compute, and metadata. Second, we can also observe this decoupling at the language frontends versus query processing, so on the front-end level. So as already mentioned, we can, for example, have tools that expose both Python data frame as well as SQL interfaces, whereas behind the scenes, the query are processed or the transformations are processed and executed in the same way. So for example, in the Apache Spark, you got data frame, data set, for example, data set in Scala, but the data frame and SQL interfaces. Similarly, for example, in Polars, so this native data frame library, you can also use like a Polars data frame API as well as SQL. We can also see that there is the decoupling from the query processing and the query execution, so the engine level. So we can observe some tools that provides single way of so different front ends, single way of query optimization. But later on, it can be executed, for example, locally in a distributed fashion or in the hybrid query. So hybrid meaning that, for example, it can be executed partially locally on a machine and partially in the cloud. This is something that, for example, DuckDB with MotherDuck service is promoting. And finally, as we said, we are observing the shift towards some native accelerators. So we can have a single processing of the query, but at the end, optimizer can choose whether we are using like a typically JVM execution runtime or all of the workloads or of the part of the workloads are offloaded to some native written in Rust, C++, or C high performance backends. But the origins of this approach are not new. It's not something that appeared this year. There was a very popular research paper released, I think, 2 years ago, entitled "Composable Data Management System Manifesto." And as you can see from the outro list, there are predominant engineers and managers from Meta, from Databricks, and other companies that in the paper tried to promote a new way of building and designing data management systems. And this is something that actually the market adopted, and I will try to show you some examples of the project that actually are following this manifesto. So they spotted that the problem with the data management systems that they are very fragmented, duplicated, and hard to maintain. So meaning that the systems are developed in parallel. So there are there is very little modularity. Various open source toolings are duplicating the code, duplicating the functionality. And the idea is pretty simple. So from the engineering perspective, it's better to modularize the system, make it use some reusable components like front end, so the API that is exposed to end users, some internal representation of the process transformation on queries. There should be dedicated or separate optimizers, as well as execution engines and runtime environments. And they are at the way that they justify that is the optimal approach is that there is a lot of already existing open source projects that can be reused, such as, for example, Apache Arrow as a memory representation. We got standardized SQL layer. We got storage file formats like, for example, Apache Iceberg. And then at the same time, we have a set of very extensible execution engines, such as Apache Data Fusion on Velox or Apache Spark, that can be used as a reusable and shareable components. And the benefits from such an approach is that these tools can evolve faster. We have a faster innovation track. Of course, we are reducing the engineering effort. And of course, since we are, for example, making all the tools have a similar user interfaces like SQL or some data frame APIs, we can make the user experience more consistent. So switching between these tools are not that hard because they are share some common ideas, some common user interfaces. And now I would like to present two projects that actually are in many cases the main building blocks of this new emerging query or execution engine. So first of all, it's Apache Arrow. Apache Arrow, I already discussed this when we presented different storage formats, but I would like to, as a recap, do it again, and because right now it would make sense when we present it as a kind of intermediate layer between different computing engines. So the basic idea is here that we have a standardized columnar memory format that have a few advantages. So first of all, because it's columnar, it's SIMD and CPU cache efficient. So we can use it as an internal representation in our tools for very quick processing with modern processors. But at the same time, since it's a standardized format, it can be very easily shared between different tools. So by doing so, we can have an ecosystem of different tools. When we, for example, do some of the processing in one tool, then, for example, pass it on to another tool. And it also makes it really possible to reuse this Apache Arrow as a main representation when we are building our tools from the scratch. So you don't need no longer need to make up your own internal representation for data. You can easily use Apache Arrow because it has also cross-language interoperability. So you can, for example, build some tools that, for example, have a Python user interface with some native backend written in Rust, and you can pass the data between these two layers without any overhead. Because all the system have a native support for Apache Arrow, and you don't longer need to copy data between these two ecosystems. To for example, programming languages, you can easily just pass the pointers and reuse the data without any overhead. And indeed, Apache Arrow is already one of the building block of very popular compute or query engines such as Polaris, Ray, Rapids, or even it's used in Apache Spark. There is also one additional project related to Apache Arrow, which is ADBC. This acronym might sound similar to you because indeed it's a JDBC and ODBC protocols replacement, but it uses Arrow, so columnar and standardized way of sharing the data between your compute engine and your consumption layer. So, for example, there is a Snowflake driver, Snowflake ADBC driver. So, by using this interface like this, you are no longer only processing data in a columnar format, like for example in Snowflake or Spark, but you can also send the data to your clients in a columnar format. So there is no longer need for any column to row transformation. So the other projects that I would like to highlight today is Apache Data Fusion. So Apache Data Fusion is basically an extensible query engine written in Rust that uses Apache Arrow as in-memory format. And as name will suggest, this is a reusable component that can be, first of all, extended with, for example, support for different file formats with some logical optimization within in its built-in query optimizer. You can also add your execution operators, add user-defined functions, transformations, table functions, and aggregation functions. So you can, if you are trying to build a new query engine or new processing engines, both distributed and or single node, you can build it. You don't need to write it from the scratch. You can take, for example, Apache Data Fusion as your starting point, use it as a starting point, and then just add the things that you need. For example, support for some custom data formats, integration with metadata catalogs, add some optimization rules to the optimizer, add some operators, and finally, couple it with some other languages because, as said, it uses internally Apache Arrow, so you can, without any additional overhead, exchange the data with some other languages. For example, if you would like to expose this your tool with some or equip your tool with some Python data frame or a similar interface. And indeed, there are a couple of tools, platforms that use Data Fusion for as their internal query engine. For example, recently announced Cloudflare R2 SQL platform is built upon Data Fusion. dbt Fusion, also a new engine for dbt, is written with Data Fusion. Arroyo, my head of that, it's a trending streaming platform. LensDB is also trending available vector DB. We also presented that during our session on storage layer. And finally, there are projects like Apache Data Fusion Comet or Apache Auron that are Apache Spark accelerators. They are both written using Apache Data Fusion. And when talking about Apache native accelerators, because this is something that I highlighted in the beginning and as one of the market trends, we do observe a couple of projects like that. So as already mentioned, Apache Data Fusion Comet, Apache Auron, Apache Gluten, Databricks Photon, or for example, Google Lightning Engine. So you can see that there are both open source projects as well as proprietary ones like Photon or Lightning Engine that tries to achieve the same. So the idea here is simple, that we are preserving this Apache Data Fusion, Apache Spark ecosystem, So still the query processing and optimization stays in Catalyst Optimizer. So the one that is available in Spark. All the integration stuff, everything is still remains as in the vanilla Spark. But we have some extensions to the Catalyst that do the JVM to native operators translations. So as you can see on the diagram on the right-hand side, we have like marked in yellow this JVM. So we got like a representation of a Spark job after the optimization done by the Catalyst. And it consists of a few steps, like, for example, file scan, filtering, join, some data exchange because there's some shuffling. And you can see that at some point of the optimization, so once the query is fully optimized at the JVM level, there is some translation step that actually switches the physical execution plan from JVM to native. And so there might be some situations when there are no all native operators are implemented. But if there is everything implemented in native, then the core query can be processed on the native part. So native meaning, of course, written in Rust or in C++. And by doing so, we can achieve two things. So first of all, according to benchmark from different projects, we can expect like a 2 to 3 times speed up over the pure JVM execution. And the other benefit of switching to this native or using these native accelerators is that in most of the cases, we can cut the memory requirements by half. So by preserving the same data frame or SQL API in Spark and just like adding this acceleration layer, in most of the cases, we can really like cut the cost of the infrastructure that is required for running that kind of queries. Yeah, so this is basically the idea behind these projects. And now this project are really getting traction. For example, Apache Data Fusion Comet is supported by Apple. They are using that internally in their data platform. Photon is something also that is highly promoted by Databricks and available in their platform. So the idea here is to like preserve the API, so you don't need to rewrite your jobs. You can just like add a few configuration parameters to your job, plus provide some additional artifacts, meaning some jars, and you can then like can switch to the native execution. This native layer is running within the same process as Spark. So actually from the end user perspective, there is no much difference when switching between these two. So these were these query accelerators, Apache Spark accelerators. So the idea here was to like preserve the Apache Spark, but add some additional accelerator that can then provide some query operators that can be used when running your transformations. But there is also a category of products that actually were built natively from the ground up. So there are no accelerators, but they are written from the scratch in the natively compiled languages such as Rust or Xebia. And we got again a couple of such a project that some of them already got really good traction, like for example Polars of DuckDB. But there are some emerging ones like Daft, Lakes, and Starrock. So let's go it by one. So Daft is a distributed query engine that is written in Rust, and they are exposing a distributed data frame interface, and they claim to be a few times faster than, for example, a Trio or some similar system. Since everything is written in Rust, but the API is exposed in Python, so it's really easy to pick up. They support multimodality, meaning that you can not only store like text or numbers, numeric values, but you can also store images. You can store, for example, vectors or embeddings, so something that you can use for running your AI pipelines. Uh, next one, the Lakeside is a very interesting project. It is still in early stage, but the idea is a kind of novel, because this time this project not only aims at adding some accelerator layer to Apache Spark. They actually tries to rewrite Apache Spark from the scratch in Rust. And again, they rely on Apache Data Fusion here. So they already got feature parity when it comes to support from most of the data frame and SQL operations. They already migrated more around 90% of unit tests from Apache Spark, and they are really growing really fast. And the initial benchmark that they are presenting shows that you can expect even more acceleration than in case of like adding some native layer to the JVM Spark. In their case, it can be even up to 8x speed up in some of the queries, with some median or medium around 4x. So it's even faster than like adding just accelerator to Apache Spark. Next is Starox. It's an MPP engine, similar to it's a kind of alternative to Trino. I think you might heard of Trino. And again, it's written in this time. It's written in C++, so not in Rust. So this is not a distributed query engine, but a full-fledged MPP engine that exposes SQL layer to end users and can be treated as a Trino or a ClickHouse alternative. And finally, we got two very already very popular projects. One is the DAGDB. So it's a single node query engine written in C++. I put a star here because it's single node, but there is a mother duck cloud platform when you can like have a kind of hybrid execution, meaning that you can use either your single node, your local execution environment, but you can, if you are using this mother duck cloud platform, you can also run your queries using more robust, more powerful single nodes in the cloud. There is also a very interesting but relatively new Duck Lake project that is again using the DuckDB engine, but this time the goal is to build a full-fledged open data lakehouse platform powered by DuckDB for query execution, and SQL and Postgres as their like a metadata layer. So it's something similar to the architecture that we are presenting here, but they rather try to keep it around the DuckDB as a query execution engine. Finally, there is a Polars project, and the goal of this project is to provide you a kind of replacement for pandas, trying to address all the pain points that pandas had. I will go into more details in a second. So this again is written in Rust, and when using this open source version, you got a single node but parallel query engine, so the same as DuckDB. But they are also starting a paid Polaris Cloud when they offer a distributed engine. So you can again like start small, running your processing locally, but once you got once you need some more computing power capacity, you can switch to Polaris Cloud and have distributed engine. Yeah, I already mentioned the Polars, so I would like to also show you using this transition from pandas to Polars to also show you some of the trends on the market and why Polars are really superior to Pandas. So first of all, the Polars idea is to expose end users with both eager and lazy evaluation. Uh, if you so the distinction between these two is that now in eager and in eager mode, the computations are triggered once you just typing them. So there is no phase of optimization or like any way of, for example, doing some kind of a smart rearrangement of your transformations. So, for example, if you take a look at the right hand side, if you are using a Pandas or Parasigar, if you got a series of operations like filtering and group by, each time you run some transformation on your data, each intermediate step is materialized. So, for example, if you are running two operations, then you need to materialize both steps in the memory. Whereas if you are using a lazy evaluation, the idea here is to group your or first of all build internal representation of your execution plan, then run some optimization on top of that, and apply some addition some optimization, like, for example, projection or predicate, push down, some simplification of transformation, combining some transformation or rearranging some transformation. By doing so, you can really have some optimized way of writing on transformation without the need for some, for example, intermediate representation, because some of the steps can be combined and run within one step. Later on, Polaris is truly multi-threaded, so there is no problem with Python anymore. And furthermore, Polaris is using arrow friendly representation, so it's columnar, and it's more friendly, for example, for storing some strings data, which are very popular when running some processing on your data. So there are no overheads as in Pandas for storing strings as objects with some additional pointers. Polaris use truly UTF native way of representing the data compatible with Apache Arrow. And finally, there is this out-of-core streaming processing, because this is very important. So in Polaris, many operations can be expressed in a streaming or out-of-core fashion, meaning that you don't need to fully materialize the intermediate results in the memory, but you can just you can process it by batch, piping the results from one operator to another. So there is no problem of, for example, in many cases, you can avoid the out-of-memory problems because the data are truly processed in chunks, so one by one. Of course, there are some operations that require collecting and materializing large fractions of data, but in many cases, you can really do it in smaller fragments, smaller batches, and the memory requirements can be significantly lower than in case of Pandas. So as a summary of this part, so we can observe that this computing ecosystem is evolving at a speed that industry really has never seen before. This is particularly driven by open standard. I'm sorry, by availability of open standards like standardized data catalogs, APIs, some standardized security mechanisms. We also have this open table file formats, and this all enables a seamless coexistence of multiple engines within one data platform. So it's no longer the case that you, for example, you need to only stick to one compute engine because there are some tightly capping between the storage formats or some security integration. Finally, distributed computing is no longer a must. Right now, you can choose. You can decide depending on your the scale of your workloads, or the amount of data or the complexity of your computations. You can choose from powerful HPC single node systems like Polaris or DuckDB, or you can choose really distributed computing engines like Apache Spark if you really require that amount of computing power for crunching your data. And because you can, people are start to really like observe the problem with like just using one large hammer like Apache Spark for all type of workloads. And by the fact that we got at our disposal, a selection of different tools for different sizes of problems, we can really by selecting the right ones for the job, we can really optimize the compute cost. Okay, so I'm handing over to Radek that will discuss the deployment options.
Hello everyone, my name is Radosław Schmidt, and I would like to tell you more about current market offering in this area of compute engines. And we will analyze many different services and their options in many different perspectives, such as payment model, deployment model, management level, and many other perspectives. At the very beginning, we have to decide whether we want to manage everything in the cloud by ourselves, or choose the ready-made managed services from market, from the vendor. In the first case, we have really free hand. We can do whatever we want. We can build our data platform like we want, with components we want. But on the other hand, we have do everything by ourselves, and we take all the responsibility for our data platform. Therefore, many companies decide to use ready-made managed services, where a large part of maintenance, development, management rests on the cloud provider, even if we have to pay more for that. The second decision we need to make is how we would like to implement our solution or deploy our solution. The basic method, of course, is well known from on-premise environment, our good old friends, virtual machines. Most organizations have really huge experience deploying their tools in this way. However, nowadays we are more often migrating to container-based approach. The most popular solution, of course, is Kubernetes, available both in on-premise and in the cloud, in the form of managed services like GKE, AKS, and many others. Popular open source tools such as Spark, Flink, Airflow, and many other tools works very well on Kubernetes, and their creators offer ready-made Docker images and Helm charts, allowing us for easy and quick installation on top of Kubernetes cluster. Most vendors, cloud vendors, also offer native Kubernetes equivalent alternative services, but they are not so popular in the data processing area. The last way in which data processing engines are provided to us in very popular and cloud native approach is serverless. In this model, our entire infrastructure is managed by the cloud provider, and we only focus on our processing, data processing, our code, and business logic. At the very beginning of so-called big data era, the processing of our data was done with the help of something called big data distributions. Originally, we used them in on-premise environments like Hortonworks Data Platform or Cloudera distribution for Hadoop. And later on, their cloud alternative appeared, such as AWS EMR, Dataproc, and Azure at the site. The first two, AWS EMR and the Google Dataproc, are created by cloud providers, by Amazon and by Google. The last one, Azure HD Insight, is a managed distribution of Hortonworks Data Platform. On this slide, we can see that, for example, AWS EMR, but also Google Dataproc, supports also three types of deployment we talked about earlier. So we can use EMR off top of EC2 instance machines, we can use our EKS Kubernetes cluster, or we can choose EMR serverless. But currently, the market is moving from big data distribution to something new. We call this a modern data platform. Unlike the big data distributions, we do not get only tools for data processing, but we got a complete data platform with all of its components. And on the left side of this slide, I have listed popular providers of such solutions. For example, we can see Databricks and Snowflake, and we can use Snowflake and Databricks with all three major cloud platforms. For example, we can use Snowflake and Databricks in AWS, in GCP, and in Microsoft Azure. The next decision we need to make is how we want to use our computing engine. The first method is Data Frame API, well known from Apache Spark, which allows us to work with Scala code or Python code. Today, however, we often use a SQL API to process our data, especially with the help of tools such dbt. In this slide, you can see really popular examples of engines, compute engines, allowing us to use SQL off top of those engines. For example, you can use AWS Athena or Redshift in AWS. We can use really popular Google BigQuery in GCP. We can use Microsoft Fabric Data Warehouse, Snowflake Warehouse, Databricks SQL Warehouse, or Starburst Galaxy. And all of those examples are supported by dbt adapters. So we can easily work with dbt and these compute engines. But if you prefer working with Apache Spark and to use Data Frame API, apart from big data distribution, of course, we have many additional services allowing us to work with Apache Spark. For example, we have AWS Glue. This is managed serverless ETL service. We have Amazon Athena to work with interactive analytics for Apache Spark. We can work also with interactive analytics using BigQuery Studio. We have also supported storage procedures in BigQuery. We can use also Databricks clusters, Microsoft Fabric, Spark Pools, or even Snowflake Snowpack. So we have plenty of options. In this slide, we can see that compute offered by Databricks offers many different options. For example, we can choose standard compute for standard Apache Spark cluster, or we can use dedicated compute for SQL. We can also choose classic deployment based on virtual machines or serverless approach managed by Databricks. Depending on the option we choose, we have the option we choose, and we have different options to work. For example, we can use only SQL in SQL warehouses, or we can pick up Scala, Python, or SQL in classic classic Apache Spark clusters. And for example, we can use Photon in all classic and serverless cluster, but in serverless clusters, we always using Photon, but in classic clusters, you can choose if you would like to use Photon or not. And of course, serverless clusters are starting really fast, about 5-10 seconds. But when we choose classic clusters, we need to wait for virtual machines provisioning in our cloud. And if we choose this classic Databricks cluster approach, we use something called Bring Your Own Cloud, where Databricks uses his own control plane to manage virtual machines located in our cloud account. The next choice we need to make is whatever we want to use, open source tools or closed source tools. We can see examples, both examples on the slide, and we have also some hybrid solution when we can use some open source tool with the help of closed source fragments. For example, when we are using Databricks Warehouse, Apache Spark is the core of their platform, and Apache Spark is, of course, open source, but Databricks Photon is closed source. So this is in some way a mix of open source and closed source solutions. And we have also something like compatible API. I mentioned about Snowflake Snowpark. Snowpark is a way to use Spark API or Pandas API on top of Snowflake vectorized query engine. So we are writing our code using Spark API or Pandas API, but everything is executed on top of Snowflake warehouse. Something very interesting, in my opinion, and really very new on the market is something called BigQuery Omni. BigQuery Omni allows us to do something like cross-cloud analytics, but you can see on this slide that BigQuery works in each of on three clouds, in GCP, in AWS, and in Azure. And this approach allows us to analyze the data located in multiple clouds accounts without the need to copy data between clouds, or because we just sending results to our BigQuery. So we do not need to copy everything or send using via network. The last thing we need to decide is payment method, payment model. And in short, we most often pay either for the operational time of our tool or for the scanned or processed data. So these two kinds of really different approaches, different pricing models. And to decrease our cost using this operation time model, we can use something like auto start or auto stop options. Sorry about my cough. And some summary on the end. Our market is really very competitive. So many tools offered by our market offer really similar capabilities. For example, Apache Spark already has SQL API, so we can work with Spark, Scala, Code, Python, or SQL. And thanks to Snowpark in Snowflake environment, they're supporting also not only SQL API, but also data frame API. However, there are still significant differences. So always we need to choose the right tool for our job. And in general, public cloud offers us really many different solutions. These are kind of building blocks for our data platform. And the last thing, open source tools are still very popular in the cloud. And in my opinion, my honest opinion, in the era of AI-powered engineering, this popularity may grow. Okay, that's all. Marek, I'm giving floor to you.
Sorry again. Yeah. So thank you, Radek, for your part. Before going into the Q&A, if there are any questions, we would like to invite you for our next webinar. That's scheduled for December 11. And this time we are going to tackle the problem of AI-assisted engineering in data lakehouse. Here is the QR code for the forum when you can enroll, so you can sign up for this webinar. So thank you for this episode. And if you got any questions, just feel free to post it on chat.
I think we don't have any questions. There are no questions here today, and this is probably the first time that we fit in an hour. Then,
Yeah.
So, in case you had some questions, please reach out after the webinar via email or on LinkedIn to one of us. And we invite for the next session. Hope to see you there. And Marek and Radek, thank you very much for leading this. This session was great. Thanks.
Thank you.
Thank you.